Section 4.4 talks about one of the uses of derivatives, modeling and optimization. What that means is we're going to use our derivatives and what we know about functions to optimize different situations and to model different situations in the real world. Basically, we're solving word problems. Now, some of you may be groaning, but remember, there's no point in doing math if you can't do word problems because all of real life is word problems. These problems are the biggest use that we'll see with the derivatives. So, optimization. What we want to do is use what we know about our local extrema on a function to be able to find maximum and minimum situations for different formulas and things that we know to relate to real life. So here's an example. You have 40 feet of fence to enclose a rectangular garden along the side of a barn. What is the maximum area you can enclose? Okay, this word right here clues us in that this is one of those problems where we're going to be using our derivatives because we're looking for a maximum, just like we were looking for on a function. Now, what we need though is a function that we can find the maximum of. So, just like any other word problem, you want to start out by drawing a picture or making a chart or something so that you can get all your data down and be able to see what's going on. So, if we have this fencing we're putting in, and we're putting it along the side of a barn, so we don't really need this side. So we have 3 sides, this fencing that we're putting in, and we have 40 feet total. So the perimeter of these 3 sides is 40 feet. So we need an equation that's going to give us what the different lengths and widths are. Well, let's call the width x. So that means both of these sides are x. So what does that mean this side is in relation to x? That's right. We take the perimeter, 40, and we subtract off what we've already used. So we have 40 feet of fence and subtract off 2x. And you have the length. So how does that help us? Well, we're looking for area. We want to maximize the area. So we need an area formula so we can maximize that function. So our area function, we'll call it a of x, equals, remember, area of a rectangle, length times width. So we have our area function here, and let's go ahead and multiply it out because it's easier to take the derivative then. Now if we want to maximize this function here, this area, we want to find what width value is, what x value is going to give us the maximum area possible. Then we're looking at the maximums on the function. If you think about it, this is a parabola that opens downward. Hopefully you remember that. And so what we're looking for is that point where we have this maximum, because this x value here is going to give us a maximum area because all the x values on our graph are the width and all the y values are the area that we've enclosed. So we want this maximum area. We want to know what the x value is to get that maximum area. So just like we were doing before, we take our derivative and find the maximum. Well, we've got to find the critical points. So we've got critical points. We're going from 0 to 40, right? X has to be between 0 and 40. And our function is defined at all places. It's just a line, so it's not undefined anywhere. So we just need to look at those endpoints and where it equals 0. So it equals 0 when x equals 10. So we set up our little chart here. We're going from 0 to 40, and 10 is the other critical point we're looking at. So we look at this and we say, well, pick a number in here, say 5. Well, that's positive. And pick a number out here, say 20. That makes it negative. So that means we're increasing and then decreasing. So it is indeed a maximum. And these endpoints here, you can check. This one's obviously going to be a minimum point, and this one's going to be a minimum point as well, because it's increasing away from it, decreasing to it. So this is our only maximum. So that means that our maximum area is with a width of 10 feet, which means that the length is what? That's right, 20 feet. So our maximum area is 200 square feet. So the biggest thing with these is you make you a chart or a picture, something where you can organize the data. Look at whether you're looking for maximums or minimums. What are you looking for the maximum or minimum of? And you need a function for that, and you need it to be in one variable. So you're going to have to relate your variables. For example, we used here that the perimeter was length plus width, and it had to be 40, so that we could get this length in terms of the width, so that we could have our area function all in one variable. So you've got to get your function in one variable. Then you look at it, well, I need to take the derivative so that I can find my critical points and test to see where I have my maximum or minimum, whichever you're looking for. Don't forget about those endpoints. And notice here, they didn't give us endpoints, but it's a logical domain. If we only have 40 feet of fence, the width can only be between 0 and 40. So you need to make sure with the word problems that you understand that there are endpoints there, just not necessarily ones that are quite as obvious. So optimization modeling. Draw your picture, make your chart, get you a function in one variable, take the derivative, decide what you need, maximum, minimum, test all that stuff, and then get your answer. Make sure with word problems, as usual, that you use your units and put units on your answers.